The first apportionment method that we're going to work with is going to be Hamilton's method. And this is actually one of the methods that uses only the standard divisor and doesn't actually bring a modified divisor into the apportionment method. So with Hamilton's method, the first thing you're going to do is find the standard divisor. And that's pretty much the first step for any of the methods that we're going to look at, is finding that standard divisor by taking the total population and dividing by the total number of seats. Then we're going to use the standard divisor to find each state's standard quota. So that's just the state's population divided by the standard quota. Then we're going to round each state's standard quota down. So in other words, we're going to award each state its lower quota. And then we're going to see how many seats we have apportioned at that point. Any that are left over are considered surplus seats, and we're then going to start awarding those surplus seats one at a time to the states that have the largest residues, or a largest fractional part, or a largest decimal part of their standard quota, however you want to think of it. And we're going to keep doing that until there is no more surplus. So let's look at the Rhode Island's House of Representatives. We want to use Hamilton's method to apportion 75 seats of Rhode Island's House of Representatives among its 5 counties. So the first thing we have to do is find the standard divisor. To find the standard divisor, we first have to find the total population. So we have to add together all of the populations of the states. And then we have to divide by the number of seats that we have to apportion. So we add together the population, we find 1,052,567, divide that by the 75 seats, and we get a standard divisor of approximately 14,034.2267. So now we have our standard divisor, and we're ready to use it to find the standard quota. To find the standard quota of each state, we're simply going to take the population and divide by the standard divisor. And what you'll find out is that depending on whether you include the decimal portion or how far you include it, it can change your standard quota slightly. So I think I carried this one out to 2 decimal places when I did my division to come up with the standard quotas. But on the MyLabs Plus, it'll actually indicate how far it wants you to round everything. So you can see that Bristol ended up with a quota of 3.5538, Kent was 11 something, Newport 5 something, so forth and so on. So now, because Hamilton's method has us awarding the lower quota originally, that's the next step for the Hamilton's apportionment method. That is to use the standard quotas we just found to award the lower quota. So for Bristol, 3.5538 is the standard quota. So the lower quota would be the standard quota rounded down, or 3. For Kent, it would be 11. For Newport, 5. Providence, 44. And Washington, 9. And you'll notice that that gave us a total of 72 representatives that have been apportioned. So how many did we have originally to give out? 75. We gave out 72 of those. So what is our surplus? Our surplus is 3. So that means we have 3 surplus seats or additional seats that we can give out, and we're going to give those out one at a time based on the fractional or residue of each of the states. So if we start comparing them, then we see that Bristol has a residue of 0.5538. Kent has a residue of 0.8395. Newport 0.9061. Providence 0.6528. And Washington 0.0478. So which of those has the largest residue? Well, remember, when you're comparing decimals, you have to compare the numbers that are in each place value. So for Bristol, the first number or digit, which is in the tenths value, is 5. For Kent, it's 8. For Newport, it's 9. For Providence, it's 6. And for Washington, it's 0. So 9 is the largest number in the tenth spot, and therefore Newport has the largest residue. And that means that we're going to give Newport the first surplus. Then we look at the remaining standard quotas and find the next largest residue. So Kent with 8 has the next largest, so Kent would get the second surplus. And we have a total of 3, so we need to give one more out. And Providence has the next highest residue with 0.6528, so Providence is going to get the third surplus. So Bristol is not going to get a surplus. Kent, Newport, and Providence will get 1 each, and Washington will get none as well. So that's a total of 3 surpluses. So our final apportionment, Bristol is going to remain with 3. Kent is going to get the 11 initially plus 1 surplus, or a total of 12. Newport is going to get 5 plus the surplus, or a total of 6. Providence will get their initial 44 plus the surplus, or 45. And Washington will get 9, no surplus, and so they'll remain with just 9. And you can see that when we add those up, we do get the correct total of 75. So notice that the final apportionment of each is within one of the lower quota, and thus this satisfies the quota rule. Now, just like with everything, Hamilton's method does have some flaws. So notice that even though Bristol County's quota has a residue of over a half, it was not able to receive a surplus. So even though an extra representative from Bristol would be much more significant than the extra representative given to Providence, or even Kent, since Bristol is so much smaller, it still doesn't get one. So if you think about it in terms of the Bristol people, you've got Providence down here is just slightly higher in the residue part than they were, and they already had 44 representatives, yet they still got an additional representative, whereas Bristol did not. So if you were from Bristol, then you might feel a little bit cheated in terms of who got the surplus seats. And that brings us to Hamilton's flaw, which is that it favors large states over small ones. All right, so let's look at another example. We have 225 nurses working in 4 shifts, apportioned by the average number of patients treated in each shift. And if you remember, we already looked at this one earlier, and we didn't have a fair apportionment at that point. We looked at lower and upper quotas and realized that the upper was too high and the lower was too low. So now we're going to look at it using Hamilton's method and find what is a fair apportionment. So we have already calculated the standard divisor, which is simply 2,700 divided by 225. We've then used that standard divisor to find each state's standard quota, which is simply the state's number of patients divided by the standard divisor. And then we've used that standard quota to find the lower quota. So now we have awarded 222 nurses. So how many surplus do we have? Well, 225 is how many we have. 222 is how many we've awarded. So we have 3 surplus seats. So we go back and look at the residual or the residue, and we see that for A, we have 0.583. For B, it's 0.75. C is 0.833. And D is 0.833 as well. So you will notice that these two are the same, and they are in fact higher than either of the others. If you only had 1 surplus seat, then you would have to carry these out further to see if there was a difference as you got out here to the further decimal values. In this case, there's not, so it doesn't really matter which one we give the first surplus to and which one we give the second surplus to, since they're both going to get a surplus either way. So surpluses 1 and 2 go to shifts C and D. And then if we look at the 2 remaining shifts, B has a higher residual than A, so B is going to get the third surplus. And then the final apportionment is going to be A keeps its 72, B gets its 85 plus 1 surplus for a total of 86. C gets 50 plus a surplus for 51, and D gets 15 plus a surplus for 16. And that gives us the total apportionment we were looking for of 225 nurses. So with our apportionment methods, there are some paradoxes that we have to consider and make sure that we keep in mind. And the first one that we're going to talk about is called the Alabama paradox. And so in 1882, Hamilton's method was used to determine the number of representatives per state using 299 seats, and Alabama got 8. Due to increasing population within the U.S. the House of Representatives was given more seats, so 300 total. So you'll see that the seats increased by 1, and then the apportionment was recalculated. And by doing so, Alabama ended up losing one of its representatives, even though no populations changed between Texas and Illinois. So what happens is, in the Alabama paradox, you add a seat or an object, so you increase the number of seats that are going to be apportioned, and that in and of itself causes a state to lose one of its seats. So you'll notice that Alabama lost a seat while Texas and Illinois both gained a seat. And so you would think that if the seats increased, then the only thing that would change is that one state would get an additional seat. But in this case, it actually caused one state to lose a seat, and then 2 states gained a seat. And so you can imagine, if you were from Alabama, you would think that was pretty unfair. And so it became known as the Alabama paradox, because Alabama lost a seat, whereas Texas and Illinois gained a seat, even though the populations remained the same. So the Alabama paradox in general is known as increasing the total number of seats by its own virtue can force a state to lose a seat. The second paradox that we'll work with is the new states paradox. So in 1907, Oklahoma joined the Union and had enough population for 5 seats. To prevent any other changes in the allocation, the House was increased from 386 seats to 391 seats. So in other words, they added a new state, Oklahoma, but they also added the seats that were needed for that new state. And the attempt there was to prevent Oklahoma from taking away seats from any other state. Well, what happened was, even with this accommodation, it caused Maine to, quote unquote, steal a seat from New York. So as you can imagine, if you were New York, the fact that Oklahoma joined the Union caused you to lose a seat probably wouldn't sit with you very well. So that became known as the new states paradox. The addition of a new state with its fair share of seats can, by its own virtue, affect the apportionment of other states. And then the last paradox that we'll look at is the population paradox. And so between the apportionment of 1900 and 1910, Virginia's population grew at an average annual rate of 1.07%, while Maine's grew at an average annual rate of 0.67%. Virginia started with more people, grew at a faster rate, and ended up with more people than Maine. But Virginia lost a representative to Maine. So the population paradox deals with population growth. So you can see that Virginia grew at a faster rate than Maine did, but still lost one of its seats to Maine. So the population paradox occurs when one state loses a seat to another, even though the first state's population increased at a higher rate than the other state. So some attributes that go along with Hamilton's method is that it's easy, it always satisfies the quota rule. It was first proposed in 1791 but was vetoed. It was part of a compromise apportionment in 1852, 62, 82, and 92. Its flaws is that it favors larger states. It is subject to the Alabama paradox. It is subject to the population paradox, and it is also subject to the new state paradox.